Hello everyone. So today we will solve problem number 5. We will analyze statically determinate frame. In this problem we have two hinge support and the reactions offered by support A are 2 and the reactions offered by support D are 2. So the total number of reactions are 4, and if you do not have internal hinge at appropriate point, the structure will be a statically indeterminate structure because we have 4 unknowns. So to have extra equation we are providing here internal hinge so that the structure becomes statically determinate structure. Okay, so we are getting one extra equation to crack the unknowns. So first we have to define the reaction here. Here it is VA, and this is HA. Here it is VD and HD. Now first we need to find this HD. To find HD, we have to take moment about point C, which is equal to 0. Moment about point C is equal to 0, and we are following a direction left to right, means D to C. If you are following a direction right to left, D to C, right to left, means clockwise moment will be negative, anti-clockwise moment will be positive. So this will not come into picture. VD, you are taking moment about point C. VD, the line of action is intersecting point C. HD, the line of action of HD is, this is the line of action of HD, and the perpendicular distance with respect to points is 4. So minus HD into 4, and you do not have any other load than this. Okay, so this is equal to 0. HD equal to 0. Now after getting HD, we can easily find HA. We have to use summation of f of x equal to 0, okay, minus HA plus this 60 minus HD equal to 0. So HA you will be getting 60 kilonewton because HD is 0. Okay, now we need to find VA. To find VA, we have to take moment about point D, which is equal to 0 because it is hinge support. So VA into 4, then HA is there. This will not come because line of action intercept with point D. This will not come. And the 60, this is the line of action of 60 kilonewton, and we are finding moment with respect to point D. The perpendicular distance with respect to point D is 4 meter, and this is creating clockwise moment plus 60 into 4. We are following a direction left to right. In that, clockwise moment will be positive, anti-clockwise moment will be negative. Then what you have, this UDL, the intensity of the UDL is 15 kilonewton per meter. Total load of the UDL is concentrated at the center. So we know how to find total load. 15 into 4, total load. This is the line of action of the concentrated load of the UDL, and this will create anti-clockwise moment. Okay, so minus 15 into 4 into 2, okay, equal to 0. So what is your VA now? VA can easily find by solving this equation. Okay, so by solving this equation, VA you will be getting minus 30 kilonewton. Now see, here we got minus. Here the direction of VA we have assumed vertically upward, and we got minus value for that. So what you do here, you take it downward VA and write it down the positive value of VA. So what you have to do here, you have to assume the direction of the reaction. If you are getting positive, then your direction is right. If you are getting negative, change the direction, okay, and make it positive. So same thing we have done here. We have assumed VA vertically upward, but we got negative value and we made it positive and change the direction of the VA. Okay, so now we need to find VD. For that we have to use summation of f of y equal to 0. Okay, so minus VA because it is going downward. Then you have this UDL. Total load of the UDL is 15 into 4. Then you have this VD plus VD because it is going upward equal to 0. Okay, so VD equal to, you will be getting VD 90 kilonewton. So this is how we need to find the reactions. Okay, now we shall start with the analysis of the members. In that we have to isolate the members and we have to solve it separately, analyze it separately. We need to find axial force, shear force and bending moment of this member. So for that you have to draw the free body diagram of member AB. Here the member AB is here. Okay, you need to draw free body diagram of AB showing load acting on the member AB, and also you have to show the reactions. We know the reaction at A, VA is vertically downward 30 kilonewton, HA is pointing towards left side, which is equal to 60 kilonewton. You know this load is given at a distance 4 meter from A and this is 2.5 meter. Okay, so we have to analyze this. We know reaction at A, we have to find reaction at B, vertical reaction and horizontal reaction at B. Okay, so what about the vertical reaction? We have to find reaction such that this member is in equilibrium. So here at A, 30 kilonewton is going downward. In order to balance with respect to vertical direction, this has to go towards upward, 30 kilonewton towards upward. Now with respect to horizontal direction, already it is balanced. 60 is going towards left side, 60 is going towards right side. If you want to find HB, you will get 0. You have to use summation of f of x equal to 0. Okay, now we can easily draw the axial force diagram. Here the axial force, the nature of the axial force is tensile in nature. We know the sign convention of axial force. If it is tensile in nature, we have to take positive. If it is compressive in nature, we have to take negative. The magnitude of axial force is 30 kilonewton and this is axial force diagram for member AB. In the same way we have to find the shear force. Now see here, left of A 0, right of A 60 kilonewton. So this is datum. Above this positive shear force, below this negative shear force. Okay, we are looking in this way. Left of A 0, right of A 60 kilonewton plus 60 kilonewton. From right of A to left of E, you do not have any force, so it will remain constant, 60 kilonewton. From left of E to right of E, this 60 kilonewton is going downward, so this will become 0, positive. So A, E, B, and you do not have any shear force here. Okay, so this is shear force diagram for member AB. So let's draw bending moment diagram. Bending moment diagram, we have to find bending moment at a different point. Bending moment at A is equal to 0, okay, because it is hinge support. bending moment at, this is bending moment at E, bending moment at E, from A to E, left to right, clockwise will be positive, anti-clockwise will be negative. Okay, 60 into 4, 60 into 4 it will be 60 into 4 it will be 240 kilonewton meter. Okay, now in the same way you have to find bending moment at B. Bending moment at B, it will be 60 into this distance. So what is this? 60 into 6.5. Okay, it is creating clockwise moment. Then you have the 60 kilonewton, and the perpendicular distance with respect to point B is 2.5, and this is creating anti-clockwise moment. So for it will be minus here, 60 into 2.5. So bending moment at B will be 240 kilonewton meter. Okay, so draw the bending moment diagram. At E it is 240, at B it is also 240, positive 240 kilonewton meter, A, E, B. So we have done with the analysis of member AB. We have calculated, we have drawn axial force diagram, shear force diagram, and bending moment diagram. In the same way, we have to analyze member BC. Okay, for that we have to draw free body diagram of member BC showing all the loads acting on member BC. Now see here, before we go for the analysis, first we have to make some balance. Okay, now see here, I will draw here AB. I know vertical reaction at B of member AB is 30 kilonewton vertically upward, and horizontal reaction is 0. Okay, so now I have to talk about balancing of joint B of member BC. Here vertical reaction is vertically upward. In order to balance joint B, here it should be downward, 30 kilonewton. So horizontal reaction is 0, no question of balancing with respect to horizontal direction. So this is done. And now see here, we have to find axial force, shear force, and bending moment. Axial force is along the member, the forces should be along the member. To find shear force, the forces should be perpendicular to the member. So here it is the UDL, the total load of the UDL is acting at the center. I can draw like this, 15 into 4. So this force is inclined. It is not along the member, it is also not perpendicular to the member. So it is very difficult to find the axial force and the shear force. We have to resolve this force along the member and perpendicular to the member. So we know this angle, we can find this angle easily. This is 2.5 meter and this is 4 meter. By using the tan formula, we can find this angle. This angle is 32 degree. This angle and this angle are equal. So this is 32 degree. Okay. Now I will draw here once again like this. This is member BC and this is the load. I will take downward here like this, 15 into 4. The total load is 60 kilonewton, and this angle, I know this angle, this is 32 degree, this angle 32 degree. So this load is inclined 32 degree with respect to perpendicular axis of the member. This axis is perpendicular axis of the member. So the resolution along the perpendicular axis will be cos, and along the member will be sine, because angle is with respect to this axis. Okay, so the resolution in this direction will be cos component and resolution in this direction will be sine component of this angle. So it will be like this, 60 into cos 32, so you will be getting here 50.8. this is 60 into sine 32, you will be getting here 31.79. so you have resolved the forces into perpendicular direction and along the member. So again I will draw like this. This is 50.8 and this is 31.79. Now you see the original load. The original load is UDL. You have resolved the UDL. You have converted it into point load 60 kilonewton, and that point load you have resolved in this direction perpendicular to the member and along the member. And now you have to convert this UDL, this point load, into UDL. How to convert that? You see here, this length we can get here, it is 4.7 meter. Okay, so what is the intensity of the UDL? Intensity of the UDL is kilonewton per meter. Okay, so the load divided by the span, you will get UDL. So we have to convert this. The intensity of the UDL is 50.8 divided by 4.7, and you will be getting this as 10.8 kilonewton per meter. Okay, and even this can be converted into UVL. Now once again I will draw like this. Member BC, we have converted the point load into UDL. We got 10.8 kilonewton per meter. We can also convert this 31.79 into UVL, because it is the resolution of the UDL and we have to divide it by the span. 31.79 divided by 4.7, so you'll get something, and this is the UVL, uniformly varying load. Or you can use this, there is no problem in this, you can use this. Okay, so these are the loads acting on member BC. Now we also have to resolve this 30 kilonewton along the member and perpendicular to the member. Along the member and perpendicular to the member, we know this angle is 32 degree and this will be 68 degree. This will be 68 degree. So now see here, I will resolve this force along the member and perpendicular to the member. The angle is with respect to along the member. So resolution along the member will be cos component and resolution perpendicular to the member will be sine component. Okay, because angle is with respect to the member. So resolution along the member will be cos component and resolution perpendicular to the member will be sine component. Okay, so along the member this is 30 into cos 68, which will be equal to 15.89, and this 30 into sine 68, which will be equal to 25.44 kilonewton. Okay, so you got this force along the member and perpendicular to the member, and we can solve for axial force and for shear force. Show the loads once again. 10.8 kilonewton per meter, 31.79. This is B and this is C. Now see here load along the member at B 15.89 is towards the joint, okay, and here 31.79 is also in the same direction. We have to find reaction here such that this member is balanced in this direction, okay. So the force 15.89 plus 31.79, which comes to 47.68 kilonewton, is going in this direction. In this direction. So in order to balance this member in this direction, this force should be against this force, the same magnitude of force, 47.68. okay. Now see here, with respect to vertical direction, 25.44 kilonewton is going downward, 10.8 we also have to find vertical reaction here. 25.44 is going downward, this entire UDL is going downward. Here we have to find BC. You can use summation of f of x, f of y equal to 0 in order to find VC. So VC you will be getting 76.2 kilonewton. You can easily find this. Now if you want to draw axial force diagram, draw datum first. Here axial force diagram for member BC. You have to see the forces along the member. At B, 15.89 is towards the joint. Towards the joint means it is compressive in nature. So we have to take minus 15.89 at B. The axial force at C is 47.68 kilonewton, which is also towards the joint. If this is the joint, if the force is towards the joint, then it is termed as compressive force. If the force is away from the joint, then it is termed as tensile force. So the compressive axial force, we are taking it as negative. At C also it is compressive in nature, 47.68 kilonewton. This is the axial force diagram for member BC. Okay, we have to draw shear force diagram. This is the datum for shear force. At left of B it is 0, at right of B this is going downward, so minus 25.44. datum below the datum means minus shear force we have to take. Then we have the next point C. Left of C, the entire UDL is going downward, so minus 10.8 into 4.7 is added to this value, so here it will be 76.22. At right of C, this force is going upward, so this will be 0 minus. So shear force diagram for member BC. Now we have to draw bending moment diagram. Bending moment at B, we know, we have calculated bending moment at B. The bending moment at B is 240 kilonewton meter. Okay, and bending moment at C, you see the original structure once again. C is internal hinge, so bending moment at C is 0, and bending moment at B we know, which is 240 kilonewton, and bending moment at C is 0. B, C. The variation of bending moment diagram will be parabola because it is subjected to UDL. Okay, so 240 kilonewton meter positive. This is the last member, member CD. Draw the free body diagram of member CD. If you want to see the reaction, D has got two reaction, HD is equal to 0 and VD is equals to 90 kilonewton vertically upward. So here we have the reaction, show the reaction 90 kilonewton, okay, and horizontal reaction is 0, and you do not have any load on member CD. We have to talk about balancing of member CD. Okay, so see, this is going upward, here it has to go towards downward, 90 kilonewton, and you can easily draw axial force diagram by this data. Towards the joint axial force is constant throughout the member, 90 kilonewton, 90 kilonewton. AFD for member CD. Shear force is 0, even bending moment is 0. Shear force diagram for member CD, bending moment diagram for member CD, because you do not have any perpendicular forces for this member so as to create shear. Okay, so you do not have any perpendicular forces, so that's the reason shear force diagram, shear force will be 0 for this member, even bending moment will be 0. At C you have internal hinge, at D you have hinge support, so at C bending moment is 0, at D also bending moment is 0. Okay, so thanks for watching this video.